Hi, this lesson is about angles, how to measure them in degree and radian measure, applications of them, and also understanding the relationship to angles on the xy plane. So, an angle is created by rotating a ray about a fixed point, a fixed endpoint called the vertex. The initial side of the ray is called the initial position of the ray is called the initial side, and the ending position of the ray is the terminal side. So a visual of what you see here, the angle is the measurement from the initial side to the terminal side. The ray are the two lines that make up the angle, and the angle measurement is this space right in here, which I'll call theta. We often use Greek letters to identify angles. So when you draw an angle, it is typical to draw it counterclockwise. So you rotate starting from the positive x-axis, and then you rotate counterclockwise. And when your angle is created in that manner, your angle measurement is a positive answer. But you can also rotate counterclockwise, meaning initial side starts on the positive x-axis, but then you go that way instead, clockwise, and in that case, your angle measurement would be negative. So typically, as I mentioned, we assign Greek letters to designate angles. So the most common Greek letter used would be theta, alpha, beta, and phi. There are others that are used, but those are the most common ones. So oftentimes also it is possible to use capital letters to designate angles. We don't usually use lowercase letters. And so the angle here on the right could be stated as angle theta because my measurement on the inside is indicated as theta, but it could also be angle B, and B referring to the vertex, that's where the two rays meet, or it could be stated as angle ABC or even CBA. It could be written in the opposite order, but you want the vertex in the middle. So all of those designations represent the same angle that you see above. So coterminal angles are angles that share the same initial side and the same terminal side. Okay, so how could that be? This is one unique angle, but you can actually represent this angle in many different ways. So, and you do that by actually rotating. Remember, you can always keep going around and round and round as many times as you want and end up at the same terminal side, starting with the same initial side. So we find coterminal angles by either adding 360 degrees or subtracting 360 degrees. So I want two coterminal angles for 55 degrees. So if you add 360, it just means that you went all the way around and then 55 degrees more. And so 415 degrees represents the same angle as 55 degrees. But you could also go clockwise by subtracting 360 degrees, and negative 305 degrees represents the same angle as 55 degrees. So in fact, all three of these, 55, 415, and negative 305, all represent the same angle. So angles can be measured in degrees or radians. So as I mentioned, one full rotation is 360 degrees, but in radian measure, it's corresponds to 2 pi radians. So 2 pi radians would represent one full rotation around a circle. Remember, a circle has a center and a radius, and the radius is the distance from the center to any point on the circle, and that radius would be the same value all throughout. So it is symmetric all throughout. So to convert from degrees to radians, we use this formula. If you want to convert a degree measure to radians, you multiply it by pi over 180. You take your degrees, multiply by pi over 180, simplify as much as possible, and that would give you your radian measure. So here are a few examples, and these are angles that are pretty common and that we should become familiar with. So we want to convert all of these angles to radian measure. So here's our calculation. So I have 30 degrees times pi over 180. The 30 goes into the 180 6 times, so you get pi over 6. Then we have 60 degrees times pi over 180. The 60 goes into the 180 3 times, so you're left with pi over 3. 180 degrees converted to radians. Well, the 180s cancel, so you're left with just pi radians. 225 degrees multiplied by pi over 180. These both have a common factor of 45, so 5 goes into 225, 45 goes into 180 4 times, so you have 5 pi over 4. 180 and 270, they have a common factor of 90, so that gives me 3, and that gives me 2, so you get 3 pi over 2. And then 330 degrees, 30 goes into both of them, leaving you with 11 in the numerator and 6 in the denominator. So 330 degrees is 11 pi over 6. So to understand where all these degrees belong, we need to understand what your measurement would be if you were to go counterclockwise. So starting here and going in that direction. So when you're on the positive x-axis, you are at 0 degrees. 0 degrees is the same as 0 radians. But if you go to the positive y-axis and end here, that means you have a 90-degree angle, because remember x and y-axis are perpendicular, and 90 degrees converted to radians is pi over 2. Then if you continue moving along and end here on the negative x-axis, that means you've gone half a circle around, which is 180 degrees, and 180 degrees is pi radians, as we found here above. And then keep moving along till we end up here at the negative y-axis. That means you've gone 3/4 of the way around. That's 270 degrees, and 270 degrees is the same as pi over 2, as we found here above. And then finally, when you make one full rotation, you end up exactly where you started. That means you've gone around 360 degrees, which is equivalent to 2 pi radians. Remember, your quadrants on your xy plane, when you go counterclockwise, this is quadrant 1, then quadrant 2, quadrant 3, and quadrant 4. So all of the angles that we wrote here actually land on one of the axes, and these are called quadrantal angles. So 0 degrees, 90 degrees, 180 degrees, and 270 degrees, and 360 degrees are quadrantal angles. Okay, and that will come up again later. But you could also have angles inside of each quadrant. Like for example, 30 degrees would be around here somewhere, 30 degrees. Okay, so let's talk more about angles and where they belong. So here, another formula that's similar. To convert from radians to degrees, you would take your radians and multiply it by pi over 180, and that would equal your degrees. So degrees, there's an extra s here, degrees equals radians times pi over 180. All right, so let's practice converting that. I want to convert all of these radian degree angles to, radian angles to degrees. So I'm going to apply this formula. So you take your radians and you multiply it by pi over 180. So the pi's cancel. The 4 goes into 180 45 times. So you're left with 45 degrees. Then we want to convert pi over 2. Again, multiply by pi over 180. Again, the pi's will cancel. 2 goes into 180 90 times. So the degree is 90 degrees. So with radians, you don't have to actually put a unit of measure, it's implied, but with degrees, we put this little circle in the upper right-hand corner to indicate degrees. All right, then we need to convert 5 pi over 6, again, multiply by pi over 180. 180 over pi. The pi's cancel. 6 goes into 180 30 times. 5 times 30 gives me 150 degrees. Then convert 3 pi over 4 times 180 over pi. Again, pi's cancel. 4 goes into 180 45 times. 3 times 45 is 135 degrees. And then finally, convert 2 pi over 3 to degrees. Multiply 2 pi over 3 times 180 over pi. The pi's cancel. 3 goes into 180 60 times. 2 times 60 is 120 degrees. Okay, an acute angle is an angle that is less than 90 degrees or less than pi over 2 radians. Remember, these two are equivalent, just different ways to measure them. Acute angles are always in quadrant 1 of a rectangular coordinate system. And that's because, remember, you go from 0 to the first quadrantal angle, which is the positive y-axis. So your acute angles will always be in quadrant 1. An obtuse angle is an angle that's more than 90 degrees or more than 3 pi over 2. Obtuse angles can be in quadrants 2, 3, or 4 of a rectangular coordinate system. And as I mentioned before, quadrantal angles are angles that are on one of the axes, the positive x-axis, negative x-axis, positive y-axis, or negative y-axis. And so they are just summarized here. And again, you have a visual of what that would look like. So given that the angles below are in standard position, meaning starting in the positive x-axis, designate each angle in degrees by the quadrant in which the terminal side lies, or state if it's a quadrantal angle. All right, so I have negative 5 degrees. Negative 5 degrees means that you have gone clockwise, so backwards. So it's a pretty small angle right in here. So negative 5 degrees is in quadrant 4. Then we look at 265. 265 is positive, which means that you are going counterclockwise, and 265 is close to the 270, but not quite. So that's the 265 right here, and that is in quadrant 3. Then we have negative 180. That means you're going again clockwise, and so negative 180 means you've gone this way, and you stop at the half circle. So that is a quadrantal angle. And then 135 degrees, that is positive. That's going to be somewhere about here. This is 135 degrees. And so that is in quadrant 2. Remember, positive angles, you go counterclockwise. Negative angles, you go clockwise. So similar exercise, except I've given you the angles in radians. Given that the angles are in standard position, designate each angle in radians by the quadrant in which the terminal side lies, or is it a quadrantal angle? So we have 5 pi over 3. So I've written my angles here counterclockwise. So just to help with some of these negative ones that I've have here, but I could also use this picture here to help me out. So one way to figure this out is to convert it to degrees. So I'm going to convert that to 180 over pi. It's easier to think in terms of degrees than radians. So the pi's cancel. 3 goes into 180 60 times, and you get 300 degrees. 300 degrees is between 270 and 360. So that would be in quadrant 4. So that's one way to approach it. Now, negative 3 pi means that I've gone around more than once. So this is negative pi, then negative 2 pi, then negative 3 pi. It's actually a quadrantal angle. It's on the 180 degree mark. So negative 3 pi over 2 is a quadrantal angle. Then we have to do 3. Now, this one might be a little harder to understand because we're used to seeing pi with radians. But we need to remember what all of these numbers mean. So pi over 2 and pi here, this is these are the boundaries for quadrant 2. Remember, pi is 3.14 approximately, and this is half of that, which is about 1.57. So 3 radians is definitely in quadrant 2. It's actually close to the 180 mark, but not quite. And then finally, we have negative pi over 2, so we can see that here, when you go in the clockwise direction, that is a quadrantal angle. Okay, so let's talk about application problems regarding angles. And all of these application problems that we're going to talk about will require that your angles be in radian measure. So there'll be application problems on arc length, area of a sector, angular velocity, and linear velocity. But this requirement is something we need to keep in mind. So if your angle is given in radian measure, you're fine. You don't need to do any kind of conversion. But if your angle is given in degrees or something called revolutions, which we'll talk about later, then we have to convert to radian measure first. Okay, so let's start with arc length. What's an arc? So an arc is a part of a circle. So it's like a piece of the rim of the circle. So we use radian measure to determine arc length, and we're going to call that arc length S for arc length. So there's a relationship between arc length and the central angle measured in radians. And so this is just a kind of showing you where the formula is coming from. Remember that the circumference of the circle, which is the distance all around the circle, is given by the formula C equals 2 pi r. And the center, and we know that the total angle measurement, if you go all the way around the circle, is 360 degrees or 2 pi radians. So we're going to set up a proportion. The arc length S is proportional to the circumference, as the central angle theta is to the total number of degrees. So S will allow us to measure this piece that we're seeing right here. Okay, so in order to develop the formula, all we have to do is cross multiply this. And when you do, you get that S is theta r, because the 2 pi's will cancel. So theta r, where r is the radius and theta is the central angle expressed in radians. Okay, we can also use radian measure to measure the area of a sector. The area of a sector of a circle is the area defined by 2 radii of a circle. Radii is plural for more than one radius. The area of the circle is also proportional to the central angle created by that sector. So as a reminder, the area of a circle, the formula is pi r squared. So the area of the circle is to pi r squared, as the central angle is to the total degrees of the circle. So A represents the area of the circle, which is exactly what you see here. So the sector is this purple piece that's colored in, and that's the area that we want to compute. When you cross multiply this and solve for A, you get this formula. A is 1/2 theta r squared, again, where theta is measured in radians, and the r is the radius of the circle. All right, so we're going to use the arc length formula and the area of a sector formula to answer the next few questions. So first question is, find the arc length where r is 21.2 centimeters and theta is 2.65. Remember, S, your arc length, is theta r. Theta is already in radians because there isn't a little degree symbol next to it. So I can just go ahead and plug this in. So I have 2.65 times 21.2, which gives me an arc length of 56.18 centimeters. And again, it's centimeters because your radius is in centimeters. So now we have to find the area of a sector where your radius is given to be 46.3 inches and your theta is again in radians as 2 pi over 5. So this time we use the formula A is equal to 1/2 theta r squared. So that's exactly what you see here, 1/2 theta r squared. So when you compute that, you get 1,346.9, and this is inches squared because we're talking about area. So your radius is measured in inches, and therefore the area is in square inches or inches squared. All right, here's another one where we have to do a little bit more. Here we want to find arc length, where I'm missing a letter here, where your area of the sector is 1200 millimeters squared and theta is 17 degrees. All right, so in order to find arc length, I have to use the formula S equals theta R. Now I know my theta, it's in degrees, so I do need to convert it, but I don't know what R is. So I have to use my area of a sector formula and using this information that's given in order to solve for R first. So that's what I did. I have A, 1200 equals 1/2 theta R squared. And remember, we're solving for R. Now notice that my theta is being multiplied by pi over 180 because I have to convert it to radians. All of these formulas require that your angle be in radians. And when you multiply and isolate R and take the square root, you get that R is 89.94. And now that I know that, I can plug it into your arc length formula. Again, remember theta is in degrees, so you got to convert it. So I have 17 degrees times pi over 180 times your radius, which is 89.94. And so you get an arc length of 26.69. And your units are millimeters because the area was in millimeters squared. Then your arc length would just be in millimeters. Okay, here's another one. A spotlight beam sweeps through a horizontal angle of 75 degrees. If the range of the spotlight is 250 feet, what area can it cover? All right, so here's your spotlight and it's beaming out. The length of that light reaches 250 feet. And they want to know what area the light covers. So I'm basically trying to figure out everything that is illuminated by that spotlight. So I basically have a triangle, an area of a sector. So I have 1/2 theta R squared. R being 250 because that's how far the light reaches. And my angle has to get converted to radians again. So when you put all of that into a calculator, you get that your area is 40,906 feet squared. All right, so let's talk about two other types of word problems. We have average velocity. The average velocity of a moving object is given by V equal to S over T, where V is the average velocity, S is the distance traveled, and T is the time elapsed. So if we use some information that we just discovered before, we know that S is the arc length or the distance traveled by a point on a circle would be theta R. So if you plug that in, you get this result for S over T. But theta over T is what we call the angular velocity. And usually we use the letter omega. This is another Greek letter in order to designate angular velocity. So the angular velocity is given by theta over T. And again, this is for theta in radians. Theta has to be in radians. So when we're considering the average velocity around a circle, we say that the velocity is not just S over T, it's actually omega R, because theta over T times R, that gets replaced by the omega, so that's omega R. And we call that formula our linear velocity. So our linear velocity is given by the formula of omega R, and this represents the relationship between the velocity v, the angular velocity omega, and the radius of a circle. So it'll be the velocity of an object moving in a circular fashion. So your omega, because your theta has to be expressed in radians, could be in radians per hour, radians per minute, or radians per second, because time could be any one of those three. All right. So oftentimes with these types of velocity problems where something is rotating, we're talking about revolutions. So just remember that one revolution represents 2 pi radians. So to convert from revolutions to radians, you just multiply by 2 pi. So 5 revolutions would equal 10 pi radians, okay, because it's 2 pi times 5. All right, so the velocity v is tangent to the circle. Tangent means that the velocity just grazes or touches the circle at a point on the edge of the circle. And the direction of velocity changes constantly as the object moves. Also, the angle theta changes with the angular velocity, which we call omega, and theta changes with respect to time. All right, so let's do some examples of these. So we have the roller on a computer printer makes 2,200 revolutions per minute. So this is a revolution, not radians. Revolutions per minute. What is its angular velocity? Remember, angular velocity is theta over t, so that's 2,200 revolutions per minute, but I need to express this in terms of radians, so I multiply this by 2 pi, and you get that the angular velocity is 13,823 radians per minute. So your unit of time should be consistent, minutes. So let's do another one. The sweep hand of a watch is 15 millimeters long. What is the linear velocity of the tip of that second hand sweep hand? So that means I'm trying to figure out what the speed is of this second sweep hand on a watch as it moves around in a circle, because we know that clocks are circular. So remember, omega is 1 revolution per minute, and so that's how long it takes a sweep hand to go around a clock. Every 1 minute, that little sweep hand goes around the clock. And if I convert that to radians multiplied by 2 pi, that means my omega is 2 pi over 1 minute. So the radius, you're told that the sweep hand is 15 millimeters long. So your velocity is 2 pi times 15, which is 94.2 millimeters per minute. So that's a rounded answer. If they wanted an exact answer, this would just be 30 pi per minute, okay? Millimeters per minute. All right, so, but second hand should be expressed in terms of seconds, not in terms of minutes, because the name kind of implies it's a second hand. And how many seconds are in a minute? Well, there's 60. So you need to divide this number by 60, and we get that the sweep hand is traveling at 1.57 millimeters per second. Okay, so let's move on to another example. This time we have a Ferris wheel that is 18 meters in diameter that makes 1 revolution in 3 minutes. Find the speed of a seat on the rim. So again, this is linear velocity because we're looking for the speed of a seat on the rim of a Ferris wheel. So therefore, that seat is moving in a circular motion. My omega is 1 revolution for every 3 minutes. Multiply that by 2 pi, you get 2 pi radians per every 3 minutes. So your velocity is omega r, and if my diameter is 18 meters, then my radius is half of that, so it's 9 meters. So you have omega r, which is 6 pi, which is about 18.85 meters per minute. That's how fast someone sitting on a seat of the Ferris wheel is traveling. Okay, here's one more. A helicopter blade is 2.75 meters long and it's rotating 420 revolutions per minute. What's the linear velocity of the tip of the blade? So again, it's something that's moving in a circular motion, meaning the blade of the helicopter, and we want to know how fast the tip of a blade is moving. So we're looking for our linear velocity. Your radius is given. The blade is 2.75 meters long. Your omega is 420 revolutions per minute. Convert that to radians, which means multiply by 2 pi. I have 840 pi radians per minute. Then V is omega times R. And when you plug that into a calculator, you get 7,257 meters per minute. Okay, so that's it for that lesson. Give the homework a try. Good luck.